Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today, we are taking a deep dive into a really fascinating topic from our unit on electrostatic potential and capacitance. We'll be talking about the effect of dielectric on capacitance, and we promise you a clear step-by-step understanding that is, completely exam-safe. So let us start with something you might have seen maybe back in class 7 or 8. We're talking about basic electrostatics. If you take a plastic comb and rub it through dry hair, you know what happens, right? It gets charged.
Oh, yes, the classic experiment. It then attracts those small bits of paper.
Exactly. But have you ever really thought about it? The comb gets charged, sure. Frictional electricity.
But the paper itself, it's an insulator. It's not a conductor. So it's always been a bit confusing. How can an electrical force pull on something that doesn't conduct electricity?
Precisely the question. That paper, or the plastic of the comb, or even glass, these materials are what physicists call a dielectric. They're electrical insulators. Now, here is the really surprising part, something that feels, totally wrong at first. When you take an insulating material like this and you place it between the plates of a capacitor, the electric field inside that capacitor actually gets weaker.
Wait, weaker? That sounds completely backwards. If the electric field, the electrical force is getting weaker, then surely the capacitor should store less charge. It feels like we're just making the device worse.
You would think so, wouldn't you? It's what intuition tells us. But the capacitor's ability to store charge, its capacitance, it doesn't decrease. It actually increases.
What? How is that even possible? Weaken the field, but increase the storage.
That's the paradox we're going to solve today. We're going to find out why adding an insulator, which seems to fight the field, actually makes the capacitor stronger. Okay, so to understand this, let's unpack the core idea with a simple analogy first. Think of capacitance C as being like the size of a water bucket, the capacity of the bucket.
Okay, I remember this analogy. So the charge, Q, is the water inside, and the potential V is like the water level or the pressure.
Perfect. So C equals Q over V. If you can store more water, Q at the same water level, V, your bucket's capacity, C, is bigger.
Yes, that's logical, more efficient.
Now, when we put a dielectric between the capacitor plates, you should imagine putting a special kind of sponge inside this water bucket.
A sponge.
But this isn't just any sponge. Electrically, it acts like a buffer. It soaks up some of the electric tension. It kind of relaxes the stress of the electric field, causing that field E to drop.
So how does a piece of plastic or paper relax an electric field? The molecules in there are neutral, aren't they?
They are. And because it's an insulator, the electrons can't just run free. But something incredible happens inside the atoms themselves. When they are hit by that strong external field from the capacitor plates, the atoms either stretch a little bit.
Stretch, like a rubber band.
Exactly like a tiny rubber band. Or, if the molecules are already polar, like tiny magnets, they rotate to align with the field. This tiny little shift of charge inside every single atom, the negative part shifting one way, positive parts the other, this is called polarization.
Okay, so all the atoms inside are stretching or turning in response to the field.
Yes, and here's the magic. This alignment of billions of atoms creates its own very small internal electric field. Let's call it EP. And this internal field, EP, always points in the opposite direction to the main field, E0. It opposes it.
Ah, so it's an opposition field. It's like the material itself is fighting back against the capacitor's field.
Fighting back is a great way to think of it. So the net electric field, the one you'd actually measure inside, is now weaker. It's E0 minus EP.
Okay, that makes sense now. The field is reduced because of this internal opposition.
Now, we connect this field reduction back to why capacitance increases. And there are two cases we have to consider. For exams, this is very important. Case 1. The battery is disconnected. So the charge Q on the plates is fixed. It has nowhere to go.
Okay, so we charge it up, then take the battery away.
Correct. Now we slide the dielectric in. We just established that the field E drops, let's say, by a factor K. Now, since potential difference, V is just the field E multiplied by the distance D, what happens to V?
Well, if E drops by a factor K, then V must also drop by the same factor K. So the new voltage is the old voltage divided by K.
Exactly. The voltage across the plates just dropped. Now look at our main formula, C equal QV. Q is constant, we said that. But V, the denominator, just got smaller.
Oh, if you divide by a smaller number, the result is bigger. So C must go up by that same factor K.
Here we have it. The new capacitance is K times the old capacitance. C equals KC0.
That's actually very straightforward when you break it down like that.
It is. Now for case 2, The battery remains connected. This means the potential V is now constant.
So the battery will work to keep the voltage fixed no matter what.
Yes, so we slide the dielectric in, the material polarizes, and for a split second it tries to reduce the field E.
But the battery is there, insisting on the original voltage V0. How does the system handle that?
This is where the battery does extra work. The moment the field drops, the potential tries to drop. To counteract this and bring the potential back up to V0, the battery immediately pumps more charge, extra Q, onto the plates.
I see. It pushes more charge to build the field back up to the strength needed to maintain that fixed voltage.
And there's your answer again. The voltage V stayed the same, but the charge Q on the plates increased. So the capacity C, CUV, must have increased. In both cases, C becomes K times C0.
So in one case, the voltage drops, and in the other, the charge increases. But the result is the same. The capacitance always goes up.
Always. Now that we've understood the physics, let's get the official wording right, the one you'll use in your exams. Could you please read the key relationship from the insert text for us?
Yes, of course. Reading. Consequently, the capacitance C increases from its value C0 when there is no medium vacuum. C equals Kc0, where K is the dielectric constant of the insulating substance. It also says the dimensionless ratio K equals epsilon 0 is called the dielectric constant of the substance.
Excellent. So K is just a number, a factor that tells you how much better that insulator is than a vacuum at this job. Let's do a very quick sum. Suppose you have a simple capacitor with just air or vacuum in between. Its capacitance is, say, 10 microfarads. Now we completely fill the space with paper, which has a dielectric constant K of about 3. What is the new capacitance?
Well, it should just be C equals K times C0, so that's 3 times 10 microfarads. The new capacitance is 30 microfarads.
It's simple as that. It now stores 3 times more charge for the very same voltage. Mid-roll branding start, Lee. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Mid-roll branding end. Now let's quickly connect this to the bigger picture. Why is this so important in the real world? Think about those massive ceramic insulators you see on high-voltage power lines.
The ones that look like a stack of discs.
Yes. Those are basically insulators being used for their dielectric properties. By stacking them, the huge voltage from the line gets divided across many units.
So the dielectric material reduces the electric stress on any single part, preventing a spark or a breakdown.
Absolutely. It manages the stress. And the second big application is miniaturization in your phone, your laptop. We need to store a lot of charge in a tiny, tiny space. We can't build huge metal plates.
So instead, we use a material with a very high K value, a good dielectric, to get a huge capacitance in a very small volume.
That's it. Without dielectrics, your smartphone would be the size of a suitcase.
So they are essential for modern electronics.
Absolutely essential. Okay, now let's focus on 2. Let's call them silent killers. These are common misconceptions that can cost you marks in the exam. First one, students often think dielectric increases the capacitance, so it must also increase the voltage V.
Yes, I can see that. I felt that earlier. Higher capacity feels like it should mean higher strength or higher voltage.
But we just proved the opposite, didn't
Yeah.
we? The dielectric is a damper. It reduces the electric field. If the charge Q is constant, the potential difference V drops. It becomes V divided by K.
Right. It makes the capacitor more efficient. It needs less voltage for the same amount of charge.
Exactly. So remember, a dielectric reduces the potential for a given charge, or it keeps it constant. It never increases it. Second silent killer, confusing dielectric constant K with conductivity. Many students see a high K value, like for water it's around 80, and they think, oh, this must be a good conductor.
That's a very easy mistake to make. High number equals good electrical properties, you know?
But it's totally incorrect. Dielectrics are, by definition, insulators. Their whole job is to block the flow of free charge. A high K just means it's very good at polarizing, at stretching its atoms, to oppose the field. But it's still an insulator. If it conducted, the capacitor would short circuit and be useless.
Understood. So I must remember, field is reduced, capacitance is increased, and dielectrics are insulators, not conductors.
That's the perfect summary. To help you remember this for life, let's use a couple of memory anchors. For the formula, C equals Kc0. The mnemonic is simple. K is king. The dielectric constant K is the king. It just multiplies the original C.
K is king. I like that. Easy to remember.
And for the concept, the catchy phrase is stuff it to store it.
Stuff it to store it.
Yes. Where you stuff the gap with an insulator to store more charge, it connects the action to the result. And finally, a physical gesture. Imagine an atom is like a sphere. Hold your hands together. When the electric field hits, just stretch your hand slightly outwards, making an oval shape. That stretching is polarization. It's the physical act that opposes the field.
Okay, that visual helps a lot. The stretch is the pushback.
Perfect. So let's summarize this entire deep dive into 3 essential exam-safe points. Point number 1, capacitance increases. The new capacitance C is always given by C equals Kc0, where K, the dielectric constant, is always greater than 1. Point 2, electric field is reduced. The dielectric polarizes, creating an internal field that opposes the external field. The net field inside becomes E equals E0 divided by K. And point 3, miniaturization. Dielectrics are crucial for making compact, high-capacity capacitors for modern electronics and for managing high-voltage stress in power systems. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROFSam, right?
Yes, ProfSam.com. Thank you for diving deep into physics with us today. Keep learning.